In this example, we are going to be considering the vector space comprised of all polynomials of degree 3 or lower. And we are going to define S to be a subset of V. S is going to be the set of all functions such that the output of the function, if we input 1, is going to be 0. So the question becomes, is S a subspace of V? So 3 axioms that we need to check here. First one is going to be axiom A4. Does S contain the 0 vector? So the 0 function, as it were, we'll call this 0 of x, is equal to 0. And the thing that I need to point out is that regardless of the input that we use, we are going to get an output of 0, and therefore this function is definitely in the subset. Then we'll check on A1, and we'll see if this thing has closure under vector addition. So we'll define 2 functions. We'll say let f1 and f2 be elements of S. As such, the property that they share is that f sub 1 of 1 is equal to 0, and f sub 2 of 1 is equal to 0. So the question becomes, would the function f1 plus f2 be in S? Now, the way that function addition is defined is that if we were to take f1 plus f2 of 1, then by definition that would be f1 of 1 plus f2 of 1. And according to what we said just a moment ago, that would be 0 plus 0. As such, when we input 1 to the function f1 plus f2, we are getting an output of 0. That is exactly the property that we're supposed to have. So f1 plus f2 would be an element of S. Therefore, we have closure under vector addition. Now, the third one is going to be scalar multiplication, and we need closure under scalar multiplication. So we'll let C be a scalar. We need to check to see if C times f1 is an element of S. So if we take C times f1 of our input, 1, then this is defined as C multiplied by f sub 1 of 1. As such, we would have C times, according to our property back here, that would be C times 0. Anything multiplied by 0 should be 0. As such, a scalar multiple of f1 is an element of S. So, because we have the 0 vector, closure under vector addition, and closure under scalar multiplication, we can draw the conclusion. Therefore, S is a subspace of V. Now, to show how this looks on the flip side of things, we are going to quite literally look at the flip side of this piece of paper. So once again, we'll define V, our vector space, to be the polynomials of degree no more than 3. This time we'll let S be the set of all functions such that when I input x equals 0, the output is going to be 1. So the question becomes, is S a subspace of V? Now, the long answer turned short would be that all 3 of these axioms are going to fail. I'm going to demonstrate how A1 fails. So we'll say let f1 and f2 be elements of this subset S. Therefore, they have the property that f1 of 0 is equal to 1, and f2 of 0 is equal to 1. In order to have closure under vector addition, I would need to be able to add these 2 functions together and get a result that is 1. However, if I were to take f1 plus f2 evaluated at 0, that would be f1 of 0 plus f2 of 0. According to the property, that would be 1 plus 1. Unfortunately, that is not equal to 1. As such, f1 plus f2 is not an element of S. Now, we only need any one of these 3 properties to break down before we are allowed to draw a conclusion about this. Therefore, S is not a subspace of V. That'll show them.